We are now going to begin to talk about galaxies, and as we did before when dealing with stars, where we started with our own sun, we're going to begin with our Milky Way. I really hope that you've had the experience of actually going out some night and seeing the Milky Way in the sky. If you haven't, try to. It is spectacular. As we look up in the sky to actually see the Milky Way, we see it as a band of light crossing the sky. Now the reason for this is because the galaxies is a relatively narrow but broad disk. And the reason why it looks so thin is because we're smack in the middle of it trying to look across that disk. We can split up our galaxy into three main components. We have the disk of the galaxy, which contains the most of everything. Then surrounding the disk we have the halo, and out in the halo we have the globular clusters, which we've talked about previously. And then at the center we also have the central bulge. Notice how it bulges out at the center. That's why we call it the central bulge. We've mentioned previously that astronomers used to like all different types of wavelengths, and because of that we've had many different studies of all different kinds of wavelengths looking at the Milky Way. In this image down here, this is actually a radio image. Specifically, it is looking at what's known as the 21 centimeter line. This is a type of radio emission given off by neutral hydrogen. So, this is tracing out where the neutral hydrogen gas is located in our galaxy. The brighter the colors are, so the reds and whites, contain a lot of hydrogen, and then there's the regions that are darker, the blues and purples, have less hydrogen. So we see that most of the hydrogen is located through the disk of our galaxy. When we turn from radio to infrared, we can actually split infrared into two regions. This top image is what we refer to as far infrared, which is infrared light that is very far from the visible spectrum. In this case, this is going to trace out the cool interstellar medium. So what regions of the interstellar medium are the coolest? And we find that there is a lot through the disk of the galaxy. The bottom image is near infrared. So this is infrared light that is actually close to the visible spectrum. Near infrared light passes through the interstellar medium fairly well, so this is going to trace out where all the stars are located in the galaxy, and we find that most stars are in the disk, but we also have quite a few in the central bulge. Alright, here is our first lecture quiz question. Which type of stars die out first? A red, B yellow, C white, or D blue? Go ahead and think about it and we'll discuss in just a bit. Alright, so what color of star dies first? The correct answer is D. Blue stars are the hottest, but the reason they're the hottest is because they have the most mass, and the higher the mass, the shorter the life. So the answer is D. Now we find that we actually have different types of stars in different regions of the galaxy. When we look out at the halo, so again, this is the region that surrounds the rest of it, we find stars that are generally old and metal poor. What we mean by metal poor is that there's less than 1% metals. And remember, we mentioned previously that in astronomy there's hydrogen, helium, and the metals. Metals are everything other than hydrogen and helium. So these stars that are relatively old and metal poor, these are referred to as population 2 stars. Population 2 stars are old and metal poor and generally found in the halo of our galaxy. So as we look out in the disk out here, notice the color. Now really quick, something I want to point out. This is not a picture of our Milky Way galaxy. It's only been within the last few years that we've finally had something actually escape our solar system, and that thing was launched in the 1970s. So if it's taken us over 50 years to finally get something beyond our own solar system, there's no chance we've actually been able to get beyond our entire galaxy. So what we often do is we'll either take a picture of some other galaxy that we think looks like our own, or we'll have an artist's rendition. We get all of the available data on what we believe is going on in our galaxy, and then we have an artist draw and paint it up for us so it looks real nice. Okay, so again, this is not an actual image of our own Milky Way. But notice, that out here in the disk, it is bluish in color. The reason that it is bluish is because of O and B type stars. Because there are a lot of those stars, and those are the ones that give off the most light, we get a bluish color to this region. As we look out in the disk, we find that these stars are generally younger and metal-rich. What we mean by that is up to 2% metals. These stars that are young and metal-rich we call population 1 stars. Population 1 are young and metal-rich and generally found in the disk of our galaxy. Our Sun is considered a population 1 star. Now notice down in the central bulge how we have a difference in color. Out in the disk it is nice and blue. Down in the bulge it's actually kind of yellowish. This shows that there are no young blue stars. We actually get a mixture of both population 1 and population 2 stars down at the central bulge. Now generally these are going to be older stars because notice all of the blue stars have died out. Because we still have a lot of blue stars out in the disk, this suggests that there's ongoing star formation, some way to keep that population of stars active. But in the central bulge, there is no ongoing star formation, which means no new O and B type stars to replace the ones that have died out. So although we do have a mix of both population 1 and population 2, they tend to be older population 1. Now, not only do we see a difference in the type of stars in the different regions of the galaxy, we also find different motions to those stars. The stars actually are moving throughout the galaxy. Out in the disk, these stars are orbiting around the center of the galaxy. They generally move in the same direction and in generally the same plane, which is why that disk is so narrow and wide. Okay, all those stars moving in a nice, nearly circular pattern. Now this diagram shows that there is a up and down wobble, and that does happen. If a star gets a little too high, then the gravity of the disk pulls it down. If it gets a little too low, the gravity of the disk pulls it back up. So they actually do bob up and down a little bit as they orbit around the galaxy. When we look out at the halo, these stars are not all moving in the same plane and not all in the same direction. So because of that, we have them going every which way. When we trace out their orbits, it creates this kind of ball shape to it. So because of that, this is referred to as the spherical component. So the halo is also known as the spherical component. Down at the central bulge, we actually have a mix of both motions. There are some stars that are orbiting in roughly the same plane in roughly the same direction, creating a disk component. But there are also other stars that have random orbits in going random directions, which create a spherical component. So just like we have both population 1 and population 2 stars in the central bulge, we also have a disk component and a spherical component down in the central bulge.